Here we have a thin film problem. You look down at some gasoline on a puddle and you see beautiful green. And the green wavelength that you see is 540 nanometers. And they tell you that, let's see, the gas's index is 1.38, the water's index is 1.33, and you assume you're in the air, where the index is 1. And what's the minimum thickness of this film of gas on the water? It's a thin film problem. Okay, so we got to think about our thin film interference. The idea here is that light comes in and bounces off the top surface of the gas, but then some light kind of goes in, bounces off the gas-water interface, and comes out like that. I'm not really drawing the angles correctly because this problem isn't about the angles. So these are the two rays that we have to think about their interference. So we're seeing green, so we want constructive interference. And you could memorize thin film formulas, or we could just set up the constructive interference case. Right? So we could say we want the difference in these two, the difference in phase, to be equal to 2 pi m. We want them to be in phase, so the difference should be an integer multiple of 2 pi. So over here, we're going to have some integer times 2 pi. And in between, remember there's the two things that contribute. There's the path difference and the potential phase differences. So the path difference is 2 pi times, right, because we're doing it in radians, so 2 pi times the physical path difference over the wavelength, basically. So the physical path difference for, if we assume small angles, is just 2t. T over the wavelength, well, that's 540 nanometers, but it's the wavelength inside the gas. So it's 540 nanometers divided by 1.38. Okay, set that part up. And now we got to think about the phase, right? So this is a reflection from low to high. So this goes through a pi phase shift. And this is a reflection from high to low. So it goes through no phase shift. We're going to get the sign right. Here we did the path of this one minus the path of that one, because we put in a positive number. Right? This path is longer. So if we did 2 minus 1, we've got to do the phases the same way, 2 minus 1. So 0 minus pi, we put a negative pi in here. And that's what we solve. So probably the trickiest part of this is knowing what to use for m. In all these classes, we always talk about m equals 0, 1, 2, but sometimes it's 1, 2, 3, and sometimes it's 1, 3, 5. It can be confusing. One thing in general, if you keep 0, that's usually for interference problems. Interference problems are fine with 0. That just means the two waves are lined up. It doesn't care why. It's just a math condition. This, usually without the 0 with just 1s, is usually when you're finding standing waves. Because if we're finding a standing wave in a tube, 0 would mean the infinite wavelength mode, which isn't really interesting. It's not really, you can't really make an infinitely long flute. And then this comes up whenever you need sort of constructive, destructive. That can be confusing as well. It should include the 0, but since they're odd, the 0 would be negative 1. Let's not make things worse. So what you got to know in this case is that you can use 0. This is an interference problem. You can use 0. The reason 0 is used a lot is because of the phase difference. Okay? If you were just talking about the path difference, and you wanted their differences to be 0, that would just be the case where you have no film, where the thickness comes out to be 0. Okay? Get rid of that, set that to 0, and t equals 0. So it's not really interesting. It also wouldn't be green because all the wavelengths would reflect the same. It would be white. What about that? But because you have the sum of a path difference and a phase difference, it's possible that you can set m equals to 0 and still get a thickness because it's the phase difference that causes the interference. So that's why we keep m equals 0 for interference problems like this. So sure enough, then, we're going to make that equal to 0, that side 0. We can divide by pi. I have this obsessive thing that I always divide by 2 pi, so I make this 1/2 why I can't get over that there. And then we can solve for t. T equals, let's see, it's going to be a fourth. It's going to be 540 nanometers over t times 1.38 times 4. Sort of an awkward way to write that, and you get 98 nanometers. And if you want to see in the book, where does it talk about this and what formula is it? It's page 579. They give the general conditions, and you'll notice they include heavy percent.